Okay, so if I have this sequence and then I want to check whether it's increasing or it's decreasing, what's the best way of doing that? Well, you know, you're talking of, is an less than an plus 1? Or if I can't try numbers, in case I'm just given the original, maybe the closed equation, then you say, okay, if I write it in function form, if I write it in the form f of x, my target is to differentiate this function with respect to x and check if the derivative is positive. If it's positive, then I'll say the sequence an is increasing. That so that the same thing should happen. Yeah, if I differentiate with respect to x and I find that it's negative, well, then I'll say it's decreasing. Basically, any sequence that is given. That's how you want to check them. Instead of trying numbers, you try this number. But then if you can't figure out these, maybe you find yourself forgetting this same principle. Then you say, okay, because I've forgotten that is to differentiate, you can just try the numbers for as long as this happens. If you want this first term here to be less than the second term, to be less than the third term, to be less than, then you know it's increasing. If the opposite is happening, then it's decreasing. Then what else do we need to know? We need to know if a sequence is alternating or not. And how do you know if it's alternating? Well, if you pick two sequences, if you pick two terms, the term an, then multiplied by the next term. If I get positive, then it's not alternating. But if when I multiply these two, then I get a number less than 0, then it means it's alternating, because this happens when the signs are different. So if the signs are the same, for example, you have plus and you have plus, then you say it's increasing. Or I have minus or minus, then I say it's not alternating. But for this to happen, you either have plus, minus, or minus, plus. Then you say, okay, it means this, the sequence is alternating. Like that. So not yet use the gadgets to do. I'm avoiding writing a lot of things because I know my board is not easy to write. Then how do you know if a sequence is bounded? Is it bounded? So a sequence will be bounded. This is where now the important things are. So you say this sequence an it will be bounded if it converges. And how does it converge? This happens if I'm able to get a limit as n goes to infinity of the sequence. So if this is less than infinity, of course you want some number, so just saying this is final, like it's a number 2, 3, 0, or anything. And then if it's divergent, then you say it's not bounded. Like that. So what else here on the sequence? I think that's what you need to know. The question now would be, if we went to the theorem sheet, When the zero sheet, we have question 1 of zero sheet 5. The one written zero sheet 8, but it's 5 inside. The first question is write the nth term for the sequences below. And you have the sequence. Sheet 8. Question 1a. So we have the sequence 1, -1 over 4, and then 1 over 9, then -1 over 16. What are we looking for? We want to write the nth term of the sequence. So a simple, for these sequences, I think the best is you always have to think a bit. So you look at the pattern. Well, if I have the first number, because of these fractions here, because of the fractions with a 1 on top, we know it's alternating in terms of signs. And then with the 1 on top, so when I'm thinking of a term, the first thing I'll do is also to put a 1 on top. So I'll put a 1 on top. And then I'm thinking I should put n down here. Okay. When I do that, then I try. If I have n is equal to 1, obviously I'll have 1 there. But if n is equal to 2, I'll have 1 over 2. If n is equal to 3, I'll have 1 over 3. So it can't match there. So it means that this should have some power. So I say, okay, let me put some, okay, it's like that. And then I put some power n. Then now I go back and check. Well, let's see what happens if n is 1. We'll have 1 over 1, which is 1. What about when n is 2? We'll have 1 over 2 to the power 2, which is 1 over 4. What about when n is equal to 3? We'll have 1 over 3 to the power 3. Then we're in trouble now because this is 1 over 27. Then we know this is not working because the third term has failed. So then you get back and say, okay, so these look like they are the squares of each position. So you come back and remove this n here. This n. I'll say, okay, where there was that n, what then do we put? Classical comfortable. So we put 2. So we put 2 here. But before that, because of the alternating one, I will need to have a -1 to the power n. Like that. Now we can try the first one. If n is 1, then the negative survives. If n is 2, then we have a negative. So then you know it can't just come direct. Just having trouble with the board. lesson was supposed to be very nice. So I bring the -1, and then I'll do n minus 1 as the power of -1. So if you check now, if I maintain the square for any, the first one we have 1. So this n here is strictly the n that starts from where n is greater or equal to 1, like that. So the first one you get 1 minus 1, that is 0. So -1 to the power 0, you get 1, which is here as a positive. We're interested in the sign here. So positive. And then you have 1 over 1, which is 1. The next one, you have 2. 2 minus 1, you get 1. Okay. So then the second one will have 2. So you have 2 minus 1, which is 1. -1 to the power 1, that is -1. And then 1 over n, we have 2 there squared, you get 4. The next one, you have 3. 3 minus 1 is 2. So I have a positive there. And then I have 3. So 1 over 3 squared, that is 9. The next one, I have 4. So 4 minus 1, that is 3. -1 to the power 3, I get a negative. And then 4 squared, that is 16. So you see that the pattern now makes sense if you use this one. So in most times, the key point is on, especially where there's a negative, you want to see what is happening to the negative. How is the negative coming in? When does it go? And the like. But you can create so many of general terms that can work. There's no unique way. Yeah. But we always just want to look at some that we're able to understand. So I'm saying this serves as a general term for part 1. Do I have serious questions from this one? Nothing. Okay. What about B? What about B? B, we have 1, then 1 over 2, then 1 over 6, then 1 over 24. Like that. So what's the general term? How are we getting these terms? 1, and then 1 over 2, and then 1 over 6, and then 1 over 24. So how are we getting those terms? So if you check, starting from this second, third, fourth, looks like it's a bit easy, where you multiply this guy. So when I have a 2, the 2 sits there. When I get a 3, I multiply my 3 by 2, I get 6. When I get to 4, I multiply by my 4 by 6. So I get 24. If I was write the next term, I get to 5. I should be able to multiply by 24 to get to the next term. So when I have the first one, so the first one is fixed. Then the second one, I'm at 2. I multiply by 1. to get 2. Then I'm at 3, I multiply by 2 to get 6. Then I'm at 4, I multiply by 6 to get 24. Now I want to write this in the general form. So I'll say the n is equal to, so that is 1 over let me put n first, like that. So that's the first thing, where n is the position, and then you multiply, so multiplying n by, I'll do this, you multiply n by 1 over n minus 1, like that. But this term is going to work starting from number 2. The first one is going to have an issue, because if I have n as 1, then this is 1 minus 1, which is 0. So everything will be vanished there. So now what I do is, I've seen that if I do the normal multiplication, things won't work. But there's always a multiplication that makes a lot of sense. Okay, so when you see that this doesn't work for all the terms, then you simply say, okay, then let me go to factorial and say, what if I have 1 over any factorial? Okay, the factorial one will help us get all the terms. So this we could get easily, except we needed to be explaining at each term, because you can see that, well, these 2, we got it by multiplying the 2 as a position multiplied by 1. 3 as a position multiplied by 2, we get 6. 4 as a position multiplied by the previous solution, 6, we get that. But then now you see, it will be hard for me to write statements on every term. So what do? I know that for me to be saying 4 multiplied by that one, then I'm talking about the factorials that drops. And then you drop now this thinking and go straight to the factorial, because this one now will help us simplify things. When n is equal to 1, you have 1 over 1 factorial. When n is equal to 2, you have 1 over 2 factorial, which is 2. When n is equal to 3, you have 1 over 3 factorial. Now 3 factorial is just 3 by 2, which is 6. Then you got 4 factorial, the next one, which is just 4 by 6. So now it makes sense in the way we are thinking, except it couldn't work for all the terms. It needed to be explained at every point. So we discard this and go for the general way, the factorial one. That's how you find the n term there. So it should be able to make sense. Okay. Next, we talk about how to check the convergence or divergence of sequences, of course. So we have, let's go straight to the tutorial sheet. This is question 2 now. Question 2a, the sequence given is an is equal to the root of n to the power 4 plus 2, so that's the root, over 2 the root of n. So you're given this question and you're trying to see how to get the, to determine whether this is whether this is this is convergent or it's divergent. And so if it converges, find the limit. But then we know that the best tool to use to check convergence is actually the limit itself. So you can start by finding the limit. Okay, so you start by finding the limit. So let's try if we are able. Of course, I can decide to write this thing as 1/2 and the root. You can combine the roots. The root of n4 plus 2 over n. And then if I divide the n inside, I'm getting something like 1/2 the root of n3 plus 1/n, like that. But then we know that if we bring in the limit, so if we say, okay, then what's the limit here? So the limit as n goes to infinity of half, I can put half this side, and then I can even put the root here, because limits do that, of n3 plus 1/n. So we understand that for n3, we retrieve back the infinite, okay? And then for 1/n, we get 0. So the limit here is infinite. And so if the limit is infinite, then we know that this does not converge. So you say an diverges. So basically, we just go straight for the limit. And then if you find, I think that that's the easiest tool to use to check if the function is divergent or if it's not. It's just having the limit. Once you have the limit, then it's divergent. If you don't have the limit, then it's not divergent. Like that. Then B, we go to B. The 1/n. The 1/n we divided. It's 2. It's supposed to be 2 inside there. So it's 2. So there's a 2 up here, not 1. That is 2. This is 2. Yeah. So 2/n, the limit there gets to 0. Okay. The next, we talk of B. B, we are talking of an being sine n over the root of n. So this one should always be, you should always be thinking of the squeeze theorem. Oh yeah, we could use L'Hopital's rule because we have infinity over infinity. But the problem with the root is that the variable doesn't get to go anywhere because it's like you're using chain rule to differentiate. That's why we must avoid it and just find other means of variety. Okay. So if I have sine n over the root of n, well, you think of the squeeze theorem. So you know that this function will always be, well, we know 1, so -1 is less than the sine of x. So now because I'm using n, let me put n. So the sine of n, which is less than 1. So if I put root n here, I should put root n here. I should put root n here. So I'll put less or equal because we are able to obtain 1 when sine is say 90. I mean when n is 90 and down when n is equal to 7. So if I have this, then I'll just get the limit. Well, as n goes to infinity of -1 over the root of n. So this gets to 0. We check also the limit as n goes to infinity of 1 over root of n. This gets to 0 as well. So it's like this is being squeezed by two functions whose limit tend to be 0. And this guy is in between these two zeros. So we have the squeeze theorem, which does the same thing as the sandwich theorem. So it's being sandwiched by the two side functions. So you say, okay, this means that the limit as n goes to infinity of sine n over the root of n is actually 0, which is less than infinity. Okay, so what does that mean? It means that we have convergence here. Okay, so we say the sequence an is convergent. And it converges to 0. So this still happens for if you have just a function sine n over n, or if I have cos n over n, the same thing will happen. And then where now we quickly rush to where we quickly rush to Peter's rule is where I have this. If I have ln over ln n over n. So this you can make it a function. If you want, you can be using the notation of a function. This is ln x over x. If I get the limit as x goes to infinity of this function, so what will happen is that if I apply the L'Hopital's rule, I differentiate the upper part, I get 1 over x. Then I differentiate the down part, I get 1. So this will give me 1 over x as a derivative. So remember, I'm still getting the limit as x goes to infinity. The limit as x goes to infinity. So this will give us 0 because of the 1 over x. So whenever I have a limit that is defined, then I know that this guy is convergent. Whatever I'm given in the sequence, I just redistribute it and then write it as a function, then it comes out like that. So it should be a bit of a boring class because of the board. So do I get any question? Looks like this has to be cutting itself in time. So when that happens, maybe let me just try and see if I can learn my board profile. You can have a long session. The teacher said he was going to send something like his own tutorial sheet, which was going to guide you on how the quizzes. I don't know if he didn't send or gave you that.